What if I told you there's a cosmic weight limit? I mean, a hard and fast rule written right into the laws of physics that decides if a dying star just fades away or if it goes out in one of the most violent explosions in the entire universe. It all boils down to one single critical number. So, what is it? What's the one thing that seals a star's fate? This is one of the biggest questions in astrophysics. And the answer, it turns out, was found by a brilliant young physicist on a long boat trip. It's this incredible story that connects the super weird world of quantum mechanics with Einstein's theory of relativity. So let's dive in and unravel this cosmic mystery. All right, here's our roadmap. We're going to start with a star's basic struggle for survival. Then we'll hit a paradox that really stumped the experts. We'll see how quantum mechanics provided a clever way out, but then relativity throws a wrench in the works. And all of that leads us right to the limit itself, and finally to the absolutely spectacular things that happen when you cross it.
Okay, first things first, to really get how a star dies, you've got to understand how it lives. And its entire life, the whole thing, is defined by this constant titanic struggle. Think of it like a massive tug of war. Pulling in one direction, you've got gravity, this relentless inward crush from the star's own incredible mass, always trying to squeeze it down to a single point. But fighting back, you have this enormous outward push from the heat and radiation blasting out of the nuclear fusion in its core. For millions, sometimes billions of years, these two forces are in a perfect, delicate balance. But what happens when the fuel for that fusion finally runs out? And that, right there, is where our mystery really begins. See, when a star like our sun dies, its core gets left behind, and it creates this totally bizarre object that presented a major paradox for one of the greatest astrophysicists of the day, Sir Arthur Eddington. These leftover cores are what we call white dwarfs, and their density is it's insane. We're talking millions of grams, literally tons of material crammed into a space the size of a sugar cube. A single teaspoon of this stuff would weigh more than an elephant. And for the physics of the 1920s, this was a huge problem. Yeah, Eddington saw the contradiction right away. Look, with its nuclear furnace turned off, a white dwarf should cool down, right? And according to all the physics they knew, as it got cooler, its internal pressure would drop, and gravity should just crush it even smaller. But they weren't collapsing. These things were stable. It was a total paradox. As he put it, it's as if a star will need energy to cool, which just made absolutely no sense. Something else had to be holding them up. And the answer, funny enough, didn't come from studying giant stars, but from the brand new, super strange world of quantum mechanics. A physicist named Rolf Fowler had the key. So Fowler figured out that there was this totally new kind of pressure, a quantum pressure. When you crush matter this densely, a rule called the Pauli exclusion principle kicks in. The best way to think about it is like a cosmic game of musical chairs for electrons. No two electrons can be in the exact same state, in the same place. So as gravity tries to squeeze them closer and closer, the electrons push back. Not because they're hot, but because there's literally no more quantum room for them to go. This creates this incredibly powerful degeneracy pressure that could fight gravity to a total standstill. Fowler had this really elegant way of putting it. He said we should stop thinking of a white dwarf as a hot gas and instead see it as one single gigantic molecule. It's locked into its lowest possible energy state. And just like a regular molecule, you just can't compress it any further. It was a brilliant solution, and it looked like it had solved Eddington's paradox completely. But turns out it wasn't the whole story. You see, Fowler's theory worked like a charm for white dwarfs up to a certain mass. But for the really big ones, the crushing gravity introduces a whole new complication, a twist in the plot that required the work of Albert Einstein himself. It's pretty straightforward, really. The more massive the white dwarf, the stronger its gravity is. That means the electrons have to push back even harder. They get forced into higher and higher energy states, which means they're moving faster and faster and faster. Eventually, their speeds get so extreme that they start getting close to the speed of light. And when that happens, well, the old rules of physics just don't apply anymore. And this, right here, is the absolute key. A young physicist named Subrahmanyan Chandrasekhar was the first person to actually do the math on what happens when you mix quantum degeneracy with Einstein's special relativity. At normal, low speeds, the pressure is really stiff. It gets way stronger with just a little bit of compression.
But Chandrasekhar discovered that at relativistic speeds, near the speed of light, the pressure becomes softer. It still pushes back, but it doesn't get stronger as quickly. And a softer pressure, well, a softer pressure can be broken.
So by combining these two monumental theories of 20th century physics, quantum mechanics and relativity, Chandrasekhar made a discovery that was as startling as it was profound. He calculated a precise, unbreachable mass limit for a white dwarf. It's about 1.4 times the mass of our own sun. Now, this isn't just some random number he came up with. This is a fundamental constant of the universe, something that emerges directly from the laws of nature. It's the absolute cosmic weight limit that electron degeneracy pressure can possibly hold up against the crush of gravity. And the implication of this was just staggering. If the leftover core of a dead star is below 1.4 solar masses, it's fine. It becomes a stable white dwarf and will just sit there cooling off for trillions of years. But if that core's mass is even a tiny bit over that limit, the degeneracy pressure fails. Gravity wins, and the star is doomed to a totally unstoppable, catastrophic collapse. Game over. So what happens then? What happens to those stars that are over the limit? What kind of fate is waiting for them when the only thing holding them up finally shatters? The Chandrasekhar limit basically acts like a cosmic sorting hat. If you're below the limit, you get a quiet retirement as a white dwarf. But if you're above it, that catastrophic collapse triggers a supernova, an explosion so violent it can briefly outshine its entire galaxy. And what's left behind? Well, it could be a neutron star, an object the size of a city that's so dense it's basically one giant atomic nucleus. Or, if the original star was massive enough, nothing we know of can stop the collapse, and it forms a black hole.
You know, years later, Chandrasekhar himself looked back on this ultimate end state. He called black holes the most perfect macroscopic objects in the universe. And what he meant was, they aren't made of messy, complicated matter. Their construction is pure. They are built only from the concepts of space and time, sculpted by gravity into their simplest, most extreme form.
And that brings us to our final thought. This limit doesn't just predict that black holes can exist, it basically demands that they must be all over the place. Any star born massive enough is destined to cross this line and end its life in total collapse, which leaves us all with this one truly mind-bending question. How many of these perfect, silent objects are out there right now, just hiding in the dark between the stars?